Florian. Great pleasure to have Florian with us today, speaking about smile dynamics and RAF volatility. Florian is at Bloomberg since 1 year, right?
Almost 2 years.
Yeah. And I knew him from before. He was a PhD student at Polytechnic with Emmanuel Gopé. So it's a great pleasure to have you here. Thank you.
Okay, so you hear me well? Yeah, okay, so thanks, Nida, for the invitation. So today I'll talk about smile dynamics and road ball. It's a joint work with Stefano De Marco from Polytechnic, and Jules Dermont is a PhD student. Yeah, maybe this is the title, we don't see. Okay, so maybe I should stand here, it's gonna be better. All right, so there's usually in the literature, people mostly focus on so-called static properties. So mainly the calibration powers of models, and I think of mostly at the term structure of the money Q. And there's been a huge literature just focusing on that, on the static properties per se, and not so much actually on the dynamic properties. So by dynamic, I mean, given the spot and the skew today, I want to understand how the implied wall surface is going to move if the spot moves. And actually, it's an extremely important question and has huge implications for market generation, but also we'll see for the delta hedging on P&L impact. And traders are very well, I mean, they're really interested in understanding how the whole surface will move if the spot moves in a certain way, up or down. All right, so this is SPX level and 1 month at the money balls. This is not the VIX, this is the 1 month, the money balls for the SPX index from beginning of 2014 until end of 2023. So we see the usual pattern will be very much like, I mean, it will be very similar if you use the VIX instead of the 1 month at the money balls. You see that, well, COVID era here, well, of course, when the SPX went down, balls tends to go up and the other way around, right? When the market is up, the balls tends to be lower. All right, moving. Oh yeah, this is the other plot of very similar patterns. If you do the Euro stock now, on left hand side, if you look at it, same pattern. So when it's up, it's down and up and down. So here we're going to look at, you see it's the 1 month, so it's a relative quantity. It's always for options whose time to maturity is 1 month. So of course, to actually compute this, you need some interpolation scheme. You don't have options that have always the 1 month maturity. Maybe it is the case now with daily options, but it might not so true for in. All right, so this is another feature or characteristics. Maybe it's obvious, but okay, I wanted to show you what is the Eurostock Smile as of date. So it's very recent. It's April 15, 2024. On the Eurostocks, we have also daily options. So it means that we have options maturing every day, end of the day, PM settled. Okay, so this is for a few maturities. This is I computed the implied force that you have C, and it's the smile as a function of log for moneyness. We see it's very steep for the very short maturities, and it tends to flatten for longer maturities. But so this is April 15th, and so this is the next day, and actually, okay, the smile has moved. I mean, this is maybe obvious, but it does move from as time evolves. And you see that the maturity of the options is the same. So the 1 day options, I mean, the 2 day option, well, it becomes the 1 day options the next day, but it does change.
So this is as of end of day?
Yeah, as of day. So there's no 0 day, right? So it's just when I mean the 1 day, the next day, the options maturing in the next.
But this is at 4 p.m.
Yes, yeah. All right, so you have to, okay, so I think you have to be precise and you need some notations and not to be very confused about a current time, which will be denoted by T, and I will denote tau, the time to maturity. It's again, I'm going to look at relative quantity. So we'll call, okay, spot price time T is ST. There's the forward, which will be, you see the FT for maturity, capital T. And so this is the very important point. First important quantity that we're going to look at is the at the money forward implied vol at current time T for time to maturity tau. So this is here. And another quantity, it's the so-called, so it's the at the money forward skew. So it is the slope. This is, I mean, if you go back to here, it's really this. It's the slope here, right? For the one. So you see, actually, it's we'll see, it's parallel as a function of tau. And there's another quantity that is also that we're going to look at is the so-called variance swap implied vol. So we know that, okay, it's in a diffusion model, if you don't have any jumps, it's actually the same thing as the log contract implied vol, right? And you can compute it from, for instance, using carbon and formula, right? Spanning formula. All right, so okay, so this is the one plot. I mean, there's nothing special about this. Maybe I should have removed the square root of T, but it's just to say that, well, if you variance swap vols and at the money vols are two different things. They typically are return structure. They can actually, it can be, if you remove the square root, it can be increasing, decreasing. There's nothing particular. It's much like discount curves, right? This is different for the skew. This is very much more stable, and we always have the shape. So I mean, Julian has also worked recently on. It's true that on some indices, notably SPX, it might not be so true now. Those days where you would have two regimes, but essentially the skew is 1 over square root. I mean, this is again, this is April 15th, so very recent data. And this is what you get for the Euro stocks, at least. So you see this, yeah, very close to 1 over square root of T. This is in a log plot, so linear regression, right? And I'm doing it the same thing using, the smile I was showing the next day. So again, it's very consistent. We still have, so you see that the exponent has changed slightly, but still it is 1 over square root. I mean, it's very, very consistent as opposed to the transfer of the variables. Again, not a lot. All right. So what I'm going to talk about? It's a quantity. It's we often refer to, known by traders and in the market by the so-called FSR or skew stiffness ratio. It was introduced by Lorenzo Bergoni. So it is essentially a spot vol covariance measure, the covariance of the spot and the volatility. So how it's defined is as this: it's simply the linear regression coefficient of the at the money vols increments onto the log spot in units of the skew. So this quantity here, it has no unit. So you see, this is the linear regression coefficient here, and you divide by the skew, the calligraphic S. We'll see how you compute this in the market, and really what we have in mind is this: it's a linear approximation of the at the money vol. So given the spot move, how the vol moves. So it's a very important for market makers, for instance, to understand. Like if today's spot is 100, if it moves by 2% tomorrow, what will be tomorrow's fall? This is important. Actually, you can maybe make more sense, and that's what I'm going to do. To estimate the SSR, you can directly consider the linear regression of the skew times the increments. The vols increments onto this quantity. So the skew is directly here on the X variable, so you don't have to normalize by the skew. So typically, we're going to look at daily increments. That's usually what we do, but I mean, you can do whatever. You can also consider maybe 5-minute increments for the money balls and lock spot. All right, so why would you be interested in this? So we'll see. So there's actually, as I said, there's a intricate links between smart dynamics and hedging. So I mean, maybe it's a surprise, but actually even hedging bananas, it's not at all obvious. Let's say you're a trader, you're risk managing options using Black-Scholes. Well, the market price C, right? It's okay. It's going to be a function of your Black-Scholes price, the spot, right? S, current spot, but also the Black-Scholes implied vol. And you see, right? If you want to compute the correct delta, well, there's the usual Black-Scholes delta that will come up, but there's also another effect. It's the vol effect. As the spot moves, the vol moves. So you have the vega term that will typically lower your delta. So I mean, traders are well aware of that. And usually I mean, they would often consider two archetypal regimes. So the so-called sticky strike, meaning that the SSR is 1. It means that the vol for a fixed strike will not move. So as the spot moves, if the strike is the same, it's the vol remains the same. And there's the sticky delta, which is a 0 SSR. And for the sticky delta, it's the same thing. Vol does not move for fixed moneyness. And all right, so actually, again, this is a relative quantity, and it might make more sense to actually look at an absolute. So if you're a trader, you have options on your book, and strike is fixed, right? So and you have a given maturity. So maybe you might be also interested in understanding, well, I don't know, not just at the money forward, but maybe 80%, 90%, 20% of spot to change to adjust for your delta. So this is what traders do. Okay, so how do you estimate this quantity practically? So you would typically look at a time window, so let's say 30 days, that's what I'm going to do later. And so you look at increments, log increments of the ticker you're interested, the spot you're interested in. This is the other money vols here that you take. So let's say daily vols, and you renormalize by this is the skew here. So and this will give you a number, dimensionless number. So this is yeah.
And you really divide by the skew at TI.
Yes.
Not T, not the.
Yeah, it's so every day you have TI, no, TI, not it's not increment, it's
I mean, other people could make another choice.
yes, yeah, you're right. So actually, okay, so it's true. So you can when you look at this, you can divide by only the skew at the current time. You might not want to do this because you're going to push too much weight on that. You can take the average of all the skews over your time window. There's many choices possible. All right. So there's a few caveats here for the SSR definition. So first thing, it depends on, I mean, non-observable quantities. Even the vols, right? It's you will need the forward implied forward, so you need to compare it. It's a bit of work to do. Maybe not so much of a problem for very liquid indices like SPX. For the skew, it's I mean, this is much a problem because I mean it is a derivative, right? So you will need to fit something at some point. And what you see is that actually a small error in the skew might get you very different values for SSR. There's also the choice of the time window. It's not so clear what L should you choose, right? And another problem also is that nowadays it's so we see, I mean, people sometimes they claim that the skew blows up, but actually it's quite the opposite those days. It's actually for some indices or stocks, it's mostly, it can be flat actually, so very close to zero. probably linked to the fact that spot and vol correlation is close to zero as well. So this is, I mean, it's SSR is not defined for a flat Q. Yeah.
So I guess the third, I mean, the middle bullet point, I guess the third item is the most important, right? The choice of the time window L.
It's not, yeah, also, yeah, you're right, but it's not.
Like 30 days or 3 months or.
Yeah, it's
you're gonna get completely different.
Yes, you're gonna, yeah, but, it's true, yeah. But it's gonna smooth out of course, the SSR you get. But, I don't know, let's say between 20 and 60 days, I mean, it's not much different actually, you will see. SSR is a
Yeah, but
very stable.
Between 20 days and 6 months, it might.
Oh, no, yeah, you're not gonna.
Very different.
Yeah, of course, yeah. People usually, would take like 30 days. It's like the vol, right? Realized vol. All right, so how do you compute it? Maybe practically it's a few graphs like to show. So, okay, so this is maybe this is something I wanted to stress as well, is that SSR has changed in recent years. So, I mean, typical values. So you start here, right? And you will end here. So we see the spot moves, at the money vols moves as well, still for Euro stocks. Okay, so it's here on the left-hand side, and on the right-hand side, what you have is the increments of the log spots here. I divide by the skew, so this is not increments, it's the current time, and y-axis you do the log vols. So this is a few points, and then you try to do a linear regression, and the coefficient would be the SSR. So 1.4, I mean, it's, so this is this was already known. It's very close to 3.5 actually, SSR. So this is for so I was using 1 month option for the 3 months options. It's very much alike. More interestingly, actually, it's those days SSR seems to be lower actually, closer to 1, actually less than 1. See, it's a 0.82. So same thing here. And this is typically the graphs you will show. So your right, it depends on the rolling window, but okay, for 30 days, so this is what you will get actually. So you see, it's fairly stable. I mean, it's close to 0.5, I would say, offers, but this is what you have. Actually, it can also be negative if you do it for Nikkei, for instance. It's you will actually get negative SSR. And this is the same graphs you would have for the 3 months market. So typically, a trader might be interested in looking at those historical time series so as to choose the SSR is going to use for his hedging. Another thing, so what I did is the average market SSR structure. So maybe I should have said that first, but you can have many models that will be calibrated to the skew, actually, or even at the money skew, right? So this is you calibrate your model to static properties, but the dynamics they will generate will be much different. So let's say you think of local vol, it will typically generate upward sloping at SSR structure. For Eastern, it might be decreasing. So it has implicate. I mean, it is ideally we would want to match this trend structure. There's nothing particular. Sometimes it can be upward sloping as well. All right. So mathematically, how do you I mean, if you want to go and compute this SSR in a model, how do you do it? So you look at covariances, Ito covariation, right? So it's defined as this. So it's the log plot at the money vols. Remember, it was current time and for time to maturity tau, and you divide by this two. All right. So this is the SSR at the money for the SSR. If we'll see that actually it's simpler to replace at the money vols are complicated objects, and it's actually simpler to look at variance swap implied vols. So you can, and that's what Bourgey actually does for having approximation. You can replace the at the money vols with the variance swap vols. And we know that as tau goes to zero, those are the same things. All right, so this is I'm taking a very general point of view, viewpoint. So I have a model for the spot price, and I'm considering forward variance models, very generic. So this is I have an n-dimensional variance motion. It's correlated with the one driving the spot, and I have a n-dimensional stochastic process. So we'll see it sort of encompass all the usual models. And I just recall that the forward variance times t for maturity u is related as this. It's the conditional spot variance times u given the information at time t, and it's related to the variance swap implied variance as this. Okay. All right. So classical examples that we're familiar with. So it's the two-factor Bourgey, for instance. So it's a log normal model for the Xi-TU. And what is important, and that was the motivation, right, of Bourgey for introducing this model, is that there's a low-dimensional representation for the Xi-TU. It's actually the deterministic function of the TU and two covariant factors, two OU processes x1, x2, so that's why it's for the two factors only. I mean, you can consider them factors if you want, but what's important is that you have this low dimensional representation. Okay, so your more classical model, I would say, it's the Heston model in forward variance model, forward variance form. You see, it's different here. It depends on the spot vol, Xi-TT, square Xi-TT. And what you have is a one-dimensional Markov representation here of the factor in the model is the spot variance itself. So it will, it's important when it's important for the SSR average computation in such a model. Now I'm talking briefly about two extension of this model, the raw model. So it's the raw Bourgey model. Here you will use a power law instead of you remember there was two exponentials before. So now you have a power law kernel. So it's a much more complicated model to study. It's still not normal in Xi-TU, but it becomes non-Markovian. So you will lose the low dimensional representation of the Xi-TU. And there's another one, which is the Roth Esten. So I'm just writing like this. Again, it's more complicated than non-Markov. And so to actually encompass all examples here, I'm considering this, the lambda, the function I was looking at as just a kernel, deterministic kernel here, and some functions that depends on Xi t, and possibly also some function here that is between t and u. It will so as to consider all models. All right, so when would you want to look at the model SSR? So maybe I will repeat myself, but again, it can be used for market scenario generation. Maybe you want also a model that will calibrate well to the skew, but possibly to the market SSR term structure, right? And also it was, I mean, Bourgey knew that, of course, from the market, he knew that he wanted to reproduce those two features, so static and dynamic features that SSR is not so far from 3.5, and it's essentially 1 over square root of 2. So that was his motivation actually for this lower dimensional two-factor Bourgey model. All right, so the first thing we can have, and maybe I'll go quickly on that, is that it's much more simpler to look at the variance swap SSR because it's essentially Ito formula for the square root, and then you will get this formula here. And what's nice is that if you assume that you have the following form for the lambda, then you get very simply this asymptotic. So you see, this is all explicit. I will show you what you get in the models before. But I should stress that actually it's known that for stochastic volatility models, this quantity goes to zero, goes to two, sorry, as tau goes to zero. And then it can be increasing or decreasing, but it converges to two. But actually in rough bone models, you can show that this is not the case anymore. It will converge to 3/2 plus h between being the Earth exponent in those rough models. So you know in classical models h is 1/2. So this is good. We get the 2. You can go. So it's not much work actually. You can just replace by known asymptotics of the skew. This is really what will change in each models, and you will get the 3/2 plus h for the Roths and Roth Bourgey. So there is a very general property for all those Roth models, and we'll see numerically that indeed it is the case. So how can you compute it in a model now? So there's no problem time window. So I mean, what you would do is this. So you will you have a Monte Carlo phase estimator. You take a very small time window, let's say delta, and you want to compute the covariance of the increments of the log with respect to these increments of the antimony balls. Same year, I mean, no, here it's just the variance, and you will compute the skew. Okay, so it's you can also compute the variance swap reply vol, for instance, in Heston it's known this form, right? And in general, it's going to require you a nested Monte Carlo to compute this, because this is what it's hard to actually evaluate. You want to compute the at the money balls, conditional on the spot move, right? This is the time delta for time to maturity and time. So this is why you will need a nesting outcome. Okay, so actually it's not so hard to compute SSR, the real SSR, not the variance swap in those low dimensional model, because you can just observe that if the psi TU is, you can write it as a function of TU and some Markovian factors, right, xt, then you know that the other manifolds will also be, they will not depend on the spot actually, and they just depend on time and those factors. So you can actually show that by Ito that this is eventually this, it's going to be the gradient with respect to the factors times this log spot factors, the covariance functions, covariation functions. And if you, so you have this formula here, and you see that actually if you multiply by h divided by h, I mean, this is true, right? This is the finite difference estimator. So you see that actually to compute SSR, what you will need is, so this is at the money balls, right? It's just, it depends on time t and the factors x. And what you will need to do is actually shift or bump the factors by a certain quantity, which is explicitly given by this one here. And you have usually this two. So essentially, to compute SSR in those models, you need 2 at the money balls and 1 skew. So what is this? In the two-factor Bourgey, so n equals 2. This function, this vector is simply this, the log spot factors covariation. So it's very simple. What you do is that you compute the antimony balls. So this is the OU processes. And what you will do is you recompute this antimony balls by shifting the OU processes for a small h. So you see it depends on the correlation of the two OU and you divide by the spot price. For Heston, it's even simpler. It does not depend on the psi anymore, and what you'll do is that you compute one at the money ball, you shift the spot variance by this quantity, this vol times the correlation. This will give you a measure of SSR. So very fast, 2 at the money balls and the skew. So this is typically what you would get. So this is model, typical models. I mean, this is market parameters for SSR. So you see at tau, time to maturity goes to 0, it goes to 2 as expected. it's very different if you replace the bar and swap, I mean, the vols by the bar and swap applied vol. And there's two things. So the FD is the finite difference. It's the one, the estimator I just showed you. And you can also compute it by Monte Carlo. They said the nested, and we do agree. This is another one. This is Heston. Again, it converges to two. Very different behavior for the bar and swap SSR and at the money for SSR. Again, this is market parameters here. And this is, so here I was taking V0 to be 10% squared. I'm changing the V0 here, and you see it's a different behavior, still converging to two. And if you increase the V0, then the bar and swap SSR and at the manifold SSR would be much like. So you get very different shapes, actually, mostly decreasing for estimates. Okay, so maybe, okay, so how would you do this in a very general for variance models?
The last graph, you also had the exact. You have the exact expression.
For the SSR? No, there's no exact, so it's, oh, no, the exact, I mean, exact, okay, it's not exact because you still need the skew. The skew you don't know, but okay, the skew you don't know, but the other quantity is only in S.
Okay, but it's quite, I mean, the blue and red, they agree quite well, but not with the exact.
No, because it's two different, it's the variance swap SSR. And this is the at the money, so they need, I mean, they should be the same. Okay. So I'm using two different estimators to estimate the same quantity, the SSR. And this is another thing, it's the but they're the same, I mean, as tau goes to zero, as they should. Okay, so how do you compute, I don't know, how much time do we have?
You have 20 more minutes, 25.
Okay, so I have, okay, so yeah, went too fast. That's fine, I can take a question. So now, okay, so how would you compute the these balls? I mean, this SSR in more general models, and notably in this ROC model. So the problem now is that you lose the low-dimensional Markovian representation, right? So it will depend on if you want the state variable now is the curve itself. It's the forward curve itself, the xi TU. But if you, so at the money for the balls, I mean, you can still write this, right? It depends on this quantity. So assume that actually you discretize it on some time grid, right, between t and t plus tau, for some, you have endpoints. Well, actually, you can show that much like what we had for the low-dimensional SSR, instead of shifting the factors, what you're going to shift is the whole curve, actually, the xi. And I mean, for those familiar, so actually, if you go to an infinite dimensional extension, this is the Frechet. I mean, it's a Frechet derivative you're differentiating with respect to a curve. But it's the same idea actually. It's I mean, this is at the money falls here, and you will recompute at the money balls by shifting the xi t given by this parameter here. And again, so you can show that actually it's equivalent to if n goes to infinity, it is this Frechet term. So
Sorry, one second.
yeah.
What's the norm on the XCT when you're taking the derivative?
What's the sorry?
You're taking a derivative with respect to the XCT, the bottom.
Oh, this one here.
Right, and so that's got to come from a normed linear space. Derivative.
Okay. I mean, it's just what I'm just saying is that okay, if you discretize it, you can show actually that it's this, And I'm claiming that if n goes to infinity, this is equivalent to taking a Gâteau derivative of to this. So yeah, it's a directional derivative.
That's, yeah, it's got the,
That's something
for sure you need a normal linear space.
yeah, okay, so I would
Sorry,
know.
that's.
Maybe it's Gâteau derivative, yeah. Anyway, in practice, you will have to differentiate the curve, and that's what you do. Because all those models that take as input instead of just these Markov factors, they take a whole curve as input, big psi. So what you will need in practice is actually to bump the curve by a certain amount. So typically this spread quantity, and
If
you
you're,
will
if you're
compute.
implementing it on a computer, it's finite.
Yeah, you're right. I would, no, and this is actually the values you get in those rough Bourgey model and the rough estimate. So you just you take the psi t and you shift it by this value here. It's again it depends on the covariance correlation actually of the log spot and the log spot and the factor which is exact. Okay, so maybe a few minutes on how you actually implement this thing. It's a bit cumbersome actually because okay, so first thing so for maybe I start with the Heston model. So Heston model, we know the characteristic function, right? We can compute the skew still using characteristic function. So this is easy. For the Monte Carlo, you can use for those that know, it's the so-called quadratic exponential scheme of Anderson. So it's very simple. For the rough Heston, it's actually work by Jim Gavril that we know actually that the characteristic function of the log spot takes the following form. Actually, this is it depends. You see, this is the state law. So on the psi t, the whole curve, psi t s, and some function g, and actually they with work with Radovicic, they use the so-called Padé approximation or rational approximation. So you just write this g function as a quotient, just the fraction of two polynomials, and it's extremely fast to compute the characteristic function. So it's very easy to do and fast to compute all those skew and ademonebles in the raw Heston as well. For the two-factor, it starts to be even though it's Markovian, it's a bit harder to compute. You will need Monte Carlo. And for the raw Bourgey, it's even worse because it's extremely hard to simulate, very slow. I mean, not extremely hard, it's the Cholesky computation everywhere, but it is slow. So if you want to, I mean, at some point you will need some GPUs if you want to have a very fast implementation. So that's what we did. And for the skew and the vols, you will need some conditioning control variant techniques. At some point because it's noisy, or you will need very high number of samples, multi-class. All right, so that's the plots you get with for instance the raw Bourgey. So this is those are the parameters. Raw Bourgey, you have spot vol correlation, spot variance. The size actually, the curve is actually flat. So you see, as expected, h is 1/2. So it's essentially a saber, and we do converge to 2 again. Again, variance swap and then the money for the SSR are very different, right? So that's what you get. When you lower the H, so that's what we wanted to see. You see, it does not converge to 2 anymore. So this is so it's H plus 3/2. So 1.5 plus 0.3, it's 1.8. And typically, yeah, it's upward sloping for the parent swap SSR and downward sloping for the money for an SSR. This is what you get for H equals 1/2. You see it starts to decrease, though, as we'll see, you need very, very, very small tau for the SSR to converge to the 1.6. For those that have actually used those rough models, so actually you need H to be small. I mean, if you want to be calibrated to market, very reasonable parameters, but it's this is where they are the hardest to simulate, more more noisy actually. And this is what we get for H equals 0.07. So this is calibrated. This is parameters taken from the paper by Christian Berger, Peter Fritz, and Jim Gavril, where they introduced this broad programming model. And we see that it seems that there's a sort of a very steep curve for the infinite derivative as tau goes to 0. This is what you have for the Roth S-burn. So using the Paddy approximation of Jim and Jim Gathron and Rowdish, and this is the market parameters that we take here. Again, it's different. It converges to H plus 3/2. This is what we have with H equals 0.1. So we see it's very different behaviors, but it seems that, so it's not so clear why, and not really understood why, but it seems that as H goes to 0, there's this steep slope occurring here for some reason. It's not so clear why now. And this is H equals 0.05. So again, parameters calibrated. So this is parameters taking from this paper here. But you see, you need extremely low value for the SSR to converge, and maybe you might actually question the numerical results, because at some point it's a very small numbers. So maybe it becomes unstable at some point. All right, so maybe I'll try to conclude briefly. So I've talked about the smile dynamics. As I said, so we know today that all the volume, I mean, 50% of the volume on options are essentially on daily options. So it might actually make sense to use possibly a spot SSR. You can use, instead of daily increments, maybe you can use 5-minute increments. You won't need the skew, of course, the 5-minute skew. There's also the computation of what is it, I mean, how do you compute SSR in local stochastic monitoring models? This is probably important for traders that do use these RSV models. Maybe you can think of other estimators, other alternatives. As we said, the SSR has some caveats. The skew, what happens if the skew goes to 0? It's actually just one number, so you might want something, maybe a whole surface of SSR, or maybe something more robust. And so the future work, so hopefully the paper should be out very soon. We're also working on deriving expansion for this SSR, so it actually makes sense to use the so-called Berger-Minion expansions and try to come up with approximation formulas, fast to implement formulas for the SSR. Yeah, I think I'll finish that here.
Thank you very much for that. Because indeed, for the computation of this SSR, you need, let's say, in its original form, you need the at-the-money volatility.
Yeah.
And you need the at-the-money skew.
Yes.
And yeah, you try to have at least close form approximation or something like that. And so indeed, like if you look at the expansion at order 2 in Volatility,
yeah,
it provides precisely the 2 quantities.
Yeah.
It also provides the curvature, by the way, for the need. And so yeah, I think it might be interesting to Because it's an expansion, so that is it's an expansion at order 2 of vol of the SMILE in generic stochastic relativity models.
Yes.
Even written in variance curve form. So it's in small vol, but in fact, even for large values of the vol, it can be very accurate. Because actually what matters is the ratio of the vol and the mean reversion is your parameter. So yeah, I think it would be very, very interesting to see how accurate the results are.
So we have a few results already, and what we've seen is that so we have approximation for the factor, for instance, they do work well for SSR. Actually, it's true that for for instance, the skew is well captured by this expansion, but the vols are not. And I mean, okay, the first result we had was that it was a bit disappointed. Expansion.
The skew maybe order 1 is enough, but for the vol itself, you should surely go to order 2.
Yes. So maybe, I don't know.
Did you go to order 2?
Yes, yeah, and we had, okay, it's, okay, maybe we still need to work on that, but it was not so, I mean, the initial results we have is not so convincing for the raw models, at least, using these expansions. Yeah, but definitely we would want a very fast implement formulas for this, for those quantities. Yeah.
And how can you make use of these results to improve the hedge or?
So typically, if you compute, okay, let's say you have you delta hedging, just a delta hedge, right? So you have you can go back, right? So typically you will have the Black-Scholes delta, the correct, but you see the at the money balls depends on the spot as well. So you will have an additional term. It will be the vega, because it's the derivative respect to the ball, the Black-Scholes, times the derivative of the balls with respect to spot. So people sometimes they call this term the backbone of the model, and this is what people call the SMILE dynamics. It's really how the balls. It's a derivative of the ball with respect to the spot, and you can approximate this with SSR times the skew. So typically SSR, let's say it's 2, 1.5, but you have the skew which is negative. So typically, if you compute this delta correction, I think people often say that it leaks, it's a leakage actually, and it will actually lower the delta. Because the vega is positive, the SSR is positive, and the skew is negative for equity indices. So typically the delta correction, I mean, it's going to lower the Black-Scholes delta, and I do think that that's what traders do actually.
You can
adjust.
justify numerically that you improve the hedge by doing that.
Yes, so that's I would have wanted to show this, but actually it's a good yeah. I wanted to you replicate motion using and see that actually you're doing better with this delta correction. Yes, but you should. Yeah.
That's good. You don't need to have underlying variance swaps in order to improve the hedge, even if you don't have a variance swap market for that.
Yeah. But I mean, yeah, it's maybe it's a surprise, but it's even computing the correct delta is not so trivial actually.
Yeah, because it's the delta under the Black-Scholes approximation.
Yes.
So it's correction.
Yes, yeah, exactly. Your risk it's just in the assumption that your risk managing with Black-Scholes, the implied vol depends on the spot. So there's an additional.
And there is no paper which does the theoretical analysis of this? Like how much error reduction do you get by doing this?
I mean, it's well known, it's correct, but I mean, it's.
In principle, I can take time step 1 over n and look at my head by doing this and see how.
I wouldn't maybe it's not.
I'm not aware.
I mean, it's so of course practitioners know this, and in Peter Brock's Anderson's book, for instance, they talk about it, and but no, theoretical analysis maybe it exists, but not aware.
But maybe another point of view is to say, oh, but this can be used to actually select the model. Because you know that in the market, the SSR is around 1.4, something like that, it's typical value. And so you would select a model that has this SSR and use the model delta to hedge. Instead of using some
Yeah,
back
yeah.
delta and using the correction.
Yeah, it's also a way of, you know, differentiating different models. Like I said, you can have many different models that have the same static property, but you want a model that will generate like, it's the same as saying it will have a better delta actually, but it's you want your model to be close to the real smile dynamics.
If there are no more questions, then let's thank Florian again. We'll have a little break, 5 minutes, while Fabrice sets his talk.